Okay, so where was I? Oh, right. So non-crossing partitions for me usually mean permutations. And the only one thing I want to draw your attention to here is that I'm using the antilinear Coxeter element. So I orient my blocks or my parts downwards. Okay, and the reason I want to talk about this before I get started is that the first thing I have for you is a unfamiliar way of generating non-crossing partitions. So I'm not claiming this is novel, but I am claiming I haven't seen anyone else write this construction down, and I would love it if any of you have, and you can tell me where. So this morning we saw that we can generate all permutations by, say, starting with the identity permutation and swapping adjacent terms, right? We start with the identity, we get everything of length 1, then everything of length 2, and finally the longest element, and this gives us the weak order. What I'm going to do is I'm going to tweak this construction just a tiny bit by saying that I'm only allowed to swap, say, the things in position I and I plus 1 if one of those letters is equal to I. So this is a strange thing to do, I think. If we start with the identity, of course, letter I is in position I, so we're always allowed to do a swap according to this condition. But now if we move to 2, 1, 3, you'll notice that 1 and 3 are in positions 2 and 3, so I'm not allowed to swap them because I don't have a 2 in either of those positions. So this is now restricted. I can't go that way. I know that's fun. 1, 3, 2, I can still swap 1 and 3 because I have a 1 in position 1, and I can make this final swap because I have a 2 in position 3, so I can swap the things in position 2 and position 3. So when I run through this, maybe coincidentally, I get the 5 non-crossing partitions of 3. Just to make sure this isn't a coincidence, let's just look at what this does for n equals 4 very quickly. So if we start with the identity, of course, we can do all of the swaps because letter I is in position I. And then we can just sort of work through on a case-by-case basis, what are we allowed to do? What are we not allowed to do? I'm not going to talk you through every single one of these. It gets a little bit tedious to even work this out. But at the end of the day, you end up with 14 permutations. And these are the non-crossing partitions again. So, sorry? Yeah, the like 1, 3, 2, 4, exactly. So if you have so 1, 3, 2, 4 in one line notation would be 3, 4, 1, 2. And so you would not be allowed to perform any swaps on this, according to my rule. And so you could think of this as sort of being in its own orbit under this operation where any swap that we try to do is forbidden. And then we have the other 15 that are connected to one another by these restricted swaps. Okay, so on a purely combinatorial level, you can prove that this operation generates all non-crossing partitions all of the time for all n. Sorry? I'm converting these permutations into cycle notation and using cycles as blocks. Did they? That's a typo. Wait, where? Which one? 3, 2, 1, 4. 3, 2, 1, 4. 4, 2, 1, 3. Yeah, I see. So 3, 2, 1, 4 shouldn't have that last arc on it. This is my mistake. Right? It should just be an arc from 3 to 1 with no other arc, because if we write it in cycle notation. Yeah. Maybe. I haven't viewed it that way, but maybe you could. Or maybe you can tell me how after the talk. Yeah. Oh, good. Okay, this is really what I was hoping for. This graph, this one right here. Okay, excellent. This is. I can't leave early. Now I expect it on Thursday. Okay. Right, so I have a combinatorial proof that this is true. It generates no insight into why it's true. It's just somehow, once you have the answer that this works, you can show that recursively you can construct every non-crossing partition by using these operations. But what I want to tell you about is why I found this, or why we found this, and why it might be a useful way to think about non-crossing partitions, even if it seems totally contrived. Now I'm going to talk about the meat of my talk, the flag variety in Schubert calculus. So this is taking a bit of a turn into the algebra geometric. So let's all remember that a flag inside of Cn is a point inside of a line, inside of a plane, inside of a 3-space, going up to the whole vector space, and that it's often useful to think about flags as cosets of the general linear group modulo the group of upper triangular matrices. And it's pretty easy to move between these two. If I have one of these matrices, I can take my ith subspace to be the span of the first I columns. If I have a flag, I can take a basis matrix for that flag, which is uniquely determined up to rescaling columns or rightward column operations, which is exactly what taking a B coset means. And so if we look at the set of all matrices, modulo B, some basic linear algebra helps us write these in canonical forms. So if I have this matrix, I can column reduce it to get a coset representative. And now I can ask, what if I were to act on the right by B? So if I were to do upward column operations, could I possibly get? And the answer looks something like this. You end up with a permutation matrix with some stars placed in it. And this is called a Schubert cell. And it's a theorem that the general linear group decomposes as a disjoint union of Schubert cells. Now, this is a topological space. I can take the closure of a Schubert cell to get something called a Schubert variety. And a very old question asks, how do two Schubert varieties intersect generically? I'm not going to tell you the answer to this. I just want to, I have to tell you this part of the story since I'm doing Schubert calculus. So the answer that modern mathematicians use is to push things over to a cohomology ring for the flag variety and compute products inside of there, which magically is the same as counting intersections of Schubert varieties. Cohomology rings are a little abstract for me. So I usually like to think about this cohomology ring as the quotient of a polynomial ring by the ideal generated by positive degree symmetric polynomials. And in this setting, classic Schubert calculus asks, if you have two polynomials in this ring, how do they multiply? There's a really nice basis that lets us compute geometric things by multiplying that basis and re-decomposing it. But this is actually not what I'm going to focus my attention on right now. If we make things a little bit more technical and work with equivariant cohomology, there is a second presentation of this ring. And for those of you who aren't familiar with these tools, I'm going to tell you a ring and we're going to care about it. There's another construction of the equivariant cohomology ring for the flag variety, which presents it as the set of polynomial-valued functions on the symmetric group, subject to a certain divisibility condition. So if I take the polynomial assigned to W, and I take the polynomial assigned to W times a transposition ij, that difference should be divisible by some difference of t's that's also determined by permutation. This is really fundamentally a combinatorial thing. So really the way I should think about this is that I have the Cayley graph for the symmetric group, like we saw this morning, and I'm placing a polynomial on each vertex, subject to the condition that whenever two vertices are connected by an edge, the difference of those labels should be divisible by some difference of t's that is determined by the label of the edge and the permutations it's connecting. So forgetting all the symmetric polynomial stuff, we now have a way of computing this ring using combinatorial data from the symmetric group. And Schubert calculus in this setting is saying, how do things multiply in this ring, for instance, with pointwise multiplication? Or how does a particular cohomology class decompose as an element of this graph cohomology ring? There are theorems that tell us how to do this again. So this isn't actually work that I ever want to do. This is just combinatorial rules that someone else has proved. I just want to give you an example of what an element in this ring looks like to make it really concrete, though. So if I have the Schubert variety for the permutation 1, 3, 2, so the permutation matrix 1, 3, 2, that would map, thanks to a theorem known as AJS Billy, to this element of the graph cohomology ring. So I'm assigning the identity permutation 0, 2, 1, 3, 0. I'm assigning the permutation 1, 3, 2, T3 minus T1, and so on. So I hope this idea is clear that we're putting polynomials on this graph, and then technically I should check that like T3 minus T1 minus T3 minus T2 satisfies some divisibility condition corresponding to that edge between those two vertices. So now I want to tell you about the new thing. So if you play with flags, you can end up recreating certain things that look a lot like the restricted symmetry condition. And so I want to tell you about one of those now. So I want to do restricted symmetry, but for flags. I've written the restricted symmetry rules I have for permutations on the screen, and I'm going to replace each of these with something that sort of is morally the same, but actually makes sense to do to a flag. So instead of swapping the ith and ith plus first entries, what I'm going to do is I'm going to replace the ith flag by any other choice of subspace that I could pick. It has to contain fi minus 1, be contained in fi plus 1, but otherwise my choice of subspace is free. And instead of this restriction that sigma I should be equal to I or sigma I plus 1 should be equal to I, I'm going to require this much more complicated looking thing. So the I minus first subspace should be contained in the hyperplane xi equals 0, and the ith basis vector should be contained in the I plus first flag. Kind of messy. I really just want you to think about these as the moral equivalent of the original restricted symmetry conditions. Here's an example of one place we could apply this. So if we look at this matrix, we look at the span of the first two columns. That span lives inside of x3 equal to 0. And if we look at the span of all columns, that of course contains the third basis vector. So according to this restricted symmetry, I can now replace these last two columns with any linear combination. So I could get this flag or that flag. So now there are infinitely many choices I could make, but I still have a well-defined operation on flags. And so I'm just going to say, let's look at everything we can get by applying this operation to the standard flag and call this QFL, quasisymmetric flag. This is a nice space. I'll run through some trivia. It doesn't mean anything to you, that's okay. It's the disjoint or non-disjoint union of certain Toric-Richardson varieties that are sort of morally equivalent to Schubert varieties. The GKM manifold, and interesting to this crowd, I hope, the permutation matrices inside of this space are exactly the non-crossing partitions. And if you restrict this restricted symmetry operation to just permutation matrices, what you get is actually the original definition of restricted symmetry that generated crossing partitions. Okay. So putting all this together and a little bit of extra work, we were able to prove that the cohomology ring of this space that I've defined for you is given by a GKM graph cohomology ring corresponding exactly to the subgraph of the Cayley graph of Sn given by non-crossing partitions. So the lattice of non-crossing partitions has a graph. And the dimension of this cohomology ring is the Catalan numbers. So just to give you a really concrete example again, this graph gave us the cohomology ring of the flag variety. And now I've thrown out my one crossing partition, and this graph gives me quasisymmetric flag variety cohomology ring. Just to make sure that we can connect this with the pictures we saw earlier in the talk, right? This is the graph I'm talking about. It's really just the refinement order on non-crossing partitions. So I want to wrap up by talking about polynomials. So I told you earlier in the talk that the cohomology ring of this space is isomorphic to polynomial ring modulo symmetric polynomials. And we were able to find something similar for our space. So using this GCAM ring construction with non-crossing partitions, we were able to show that the cohomology ring of the quasisymmetric flag variety is the polynomial ring modulo quasisymmetric polynomials. And the equivariant cohomology ring is polynomials in two variables modulo a new set of equivariant quasisymmetric polynomials. If you know what quasisymmetric polynomials are, great, this can be the theorem. If not, I want to give you a final definition for what those are using restricted symmetry. So restricted symmetry for the third time, now using polynomials. So my conditions, I'm going to replace them with something morally equivalent one more time. So now my swapping operation will just be swap variables I and I plus 1. And so if I were to insist that a polynomial is invariant under this operation with no restrictions, I would get symmetric polynomials. And now I'm going to add a restriction that either xi or xi plus 1 should be equal to 0. So this is my restriction now. And it turns out that quasisymmetric polynomials are exactly the invariants under operation 1 subject to 2. And I think condition 2 is a little it's sort of hard to understand. So I just want to give you a really clear example. So x1 squared plus, or x1 squared times x2, x1 squared times x3, x2 squared times x3 is a quasisymmetric polynomial. And we can verify it using this definition by checking that f of x1, 0, x3 is equal to f of 0, x1, x3, and f of x1, x2, 0 is equal to f of x1, 0, x2. So this is what I mean by you're allowed to swap these inputs if one of them is 0. Okay. The equivariant version of this theorem or definition is basically the same. The only difference is that now I set my xi's equal to ti instead of I recover a definition of equivariant quasisymmetry that makes this cohomological true. Final corollary, the space of equivariant quasisymmetric polynomials is exactly the set of polynomials in two sets of variables, x's and t's, which satisfy the condition that when I evaluate the x's at t's corresponding, oh, this is a typo. These should be t's. F of tw1, f of tw2, f of twn should be equal to 0 for all non-crossing w. Somehow this is a vanishing condition on all non-crossing partitions. Okay. And so just to leave you with a short summary of what I told you about, there's this very nice picture involving the flag variety, the Cayley graph of the symmetric group, and symmetric polynomials. And using restricted symmetry and non-crossing partitions, we were able to reproduce it and create a similar story using the quasi-symmetric flag variety, the GCAM ring on the lattice of non-crossing partitions, and quasi-symmetric polynomials. There's a bunch of other nice things that go into this story that are just a little too big to fit into this talk. But this story on the left has Schubert varieties, it has Schubert polynomials, it has interesting products, it has a theorem called AJS-Billy, and on the right we have analogs of each of those. So if you know this theory and you're interested in any of these, ask me about it and I'll tell you what the analogous non-crossing version is. That's all. Thank you for listening. These are still in commuting polynomials. So I think these ones are, whereas the ones you're talking about are non. I haven't compared them closely, but I've compared them. Certainly different things. Mm-hmm. I haven't looked into that. I don't. One of my collaborators is sitting right behind you. Philippe, do you? Okay, no. Oh yeah. It's like it looks something like this. So yeah. So we have thought a bit about it. There's an obstacle, which isn't necessarily an obstacle to this story working, but is an obstacle to this being a definition of non-crossing partitions, which is that, so this thing here relies on the fact that non-crossing partitions are a connected graph in the weak order. And this isn't true in other types necessarily. So you can't just pull this same trick and get non-crossing partitions out of it. Maybe you get some other interesting set of permutations, but there's a basic obstacle that we haven't gotten. Mm-hmm. How sensitive is it? Be sure. I should be careful. No one has asked me this question in all of the talks about this I've given. But I'm almost certain that the GKM result, so the GKM graph cohomology ring works because a torus stable affine paving. And that works in any field. And so maybe there's an assumption in GKM that I should be careful about. Without saying this is true, I feel very strongly that this is as close to independent of the field as one can hope.